All right, we are finally live again. A big hello to everybody. We're going to give everybody just a moment to just log in as we're getting ready to go into our live office hour with Jake, focusing on algebra and pre-calculus today. I am excited to have everybody here, and we're going to be live in just 1 minute. Looks like some people are just starting to log in, so we'll go ahead and get started officially. A big hello to everyone who's rolling in. Welcome to our live office hours for pre-calculus and algebra, brought to you by Chegg. I'm at Wallace. You probably recognize me from my channel using the same username at Wallace on YouTube, Instagram, TikTok, and the like. I'm excited to have you here, though, partnering with Chegg. For those of you that have joined us for our live events before, we are so excited to have you back. But for those of you that are here for the first time, the goal here today is to think about this and like a virtual office hour. You can kind of think we're here today to help you understand pre-calculus and algebra better. In fact, I'm going to be here every week at this time. It is 5 o'clock Pacific time, 8 o'clock Eastern time on Wednesday. So mark your calendar so you can join us every week to ask all of your best questions for algebra and pre-calculus. So don't be shy, drop them in the chat, and I'll try to answer as many questions as come in. Basis for a linear system of equations is linear algebra. We're not going to go to linear algebra. We're going to keep it to like algebra of functions. So sorry, we'll save that for the algebra office hour. That's beyond the scope of what we want to talk about today. But we can take a look at a system of equations if you would like. So why don't we start off with that since you brought it up? It's a great opening topic. Let's say I've got a system of equations like x plus 3y equals 7 and 2x plus 4y is 10. Let's go with that. Now, the nice part about system of equations is we actually have lots of ways to solve them, to solve for x and y. One way that we can solve them is we can solve it with a substitution method. The idea of substitution is if I can get one variable all alone, then I can plug that into the other equation in order to solve it. So I can get this x all alone really quick by subtracting 3y from both sides. When I do that, we end up with x equals 7 minus 3y, which means anywhere I see an x, I can replace it with 7 minus 3y. So that's what we're going to do in this other equation. We've got 2 times x. That's going to be 2 times the 7 minus 3y. Plus 4y is equal to 10. And that gives me an equation with just one variable that we know how to solve. We can solve this by distributing the 2 through the parentheses. 2 times 7 is 14. 2 times 3 is 6y. Plus 4y equals 10. Let's go ahead and combine some like terms. So we have 14 minus 2y. Combining those y's together equals 10. And that makes it into a simple two-step equation that we know how to solve. Subtracting 14 from both sides gives us negative 2y equals negative 4. Divide by negative 2, and y is equal to a positive 2. Now that we know y, how do we get the x? Well, we get the x by plugging that y into our x equals equation, because wherever we see a y, we can replace it with that 2, and that's exactly what we're going to do here. X is equal to 7 minus 3 times y, or 3 times 2, or x is equal to 7 minus 6, which means x is equal to 1, y is equal to 2. We have solved this system of equations. Excellent. A lot of great questions starting to come in. Go ahead and keep your questions coming. Remember, this is your office hour for algebra and pre-calculus. So what algebra and pre-calculus questions do you have? Stick them in the chat. We'll do our best to answer as many of them as we can. I see a couple questions about calculus coming in as well. That's not really what we're doing on this hour, but tomorrow at I think it's 4:15 Pacific time, 7:15 Eastern time, there's going to be a calculus study session you'll have to join us for. If you scan this QR code up in the corner, you can get the full schedule of what we're doing with our lives and our topics. And before I step away from this question, though, I want to back up and answer it a second way. I mentioned there's lots of ways to solve systems of equations. There's even ways that I'm not going to talk about here, including matrices, inverses, Cramer's rule, lots of other options. One other way, though, to solve a system of equations is if we can get opposite numbers in front of the x or opposite numbers in front of the y, those will subtract out to 0. Let's look at how that works by multiplying this first equation. There's a positive 2 here. I want a negative 2 up here. So we're going to multiply by negative 2 on both sides, which is going to give me negative 2x, negative 6y, and negative 14. Which is really nice because now I can add the columns together. Combining the x's gives me 0. Combining the y's gives me negative 2y. Combining the numbers after the equals gives me negative 14. Divide both sides by negative 2. And we find out y is equal to a positive 2. Same answer we got before. So really, we've got multiple ways to go about solving. One is by this method. It's called elimination because we eliminated the x's. The other way is called substitution because we substituted in the value for x. And there's a third way called graphing. And I want to take a look at graphing because Zach on TikTok wanted to know about graphing a function. So he didn't specify what type of function. So that really kind of opens up. We could spend a whole week on how to graph different types of functions. Because if we know certain properties about those functions, we can go ahead and graph them. So for example, let's say I want to graph, we'll start simple and we'll build up. Let's say I want to graph y equals 1, let's go 2/3 x minus 4. This is a linear equation. And we know a linear equation is of the form y equals mx plus b, where b is the y-intercept and m is the slope, the rise over the run. So if I wanted to graph this linear function, we'll give ourselves a little grid here. Hopefully we got enough tick marks on here. When we're graphing this linear function, b is where the graph starts. Our starting point here is negative 4. So on this y-axis, we're going to start down here at negative 4, and then we're going to move to our next point using our slope, which is this fraction up front, the rise over the run. We're going to rise 2 from our point and run 3. So I rise up 2 and run 2, 3. There's another point. Rise up 2, run 3. There's another point. I can even go backwards. I can rise negative 2 and go backwards 3 to get another point. And that's going to give me this line here. And that line is a picture of solutions. Any point on that line is a solution to that equation. Now, I mentioned that's kind of the basic function. We can do more complex functions. We have these things called conics that we like to graph. And so let's look at a more interesting conic section. Should we try a parabola? Let's graph y equals 3x squared minus 6x plus 5. And I don't know if this is going to graph nicely. Let's go ahead and we're going to complete the square on this just to give us some practice with completing the square. And that will also put this equation into what we call vertex form, because those vertexes will tell us where the graph starts and where the graph goes. So to get it in vertex form, we're going to focus on the first 2 terms, factor out the 3 because we need to have 1 in front of x squared. When I do, I get 3 times x squared minus 2x. And then we're going to make this little piece into a perfect square. And the way we can build it into a perfect square is we take this middle number, find half of it, we get 1, and then we square that answer. 1 squared is 1, so I'm going to add 1. But to stay balanced, I'm also going to subtract 1. But I have to be actually a little careful because that 1's in parentheses. Technically, it's also getting multiplied by the 3 if I were distributed. So we have to take this negative 1 and also multiply it by 3. The reason we do that is now it's a perfect square. This thing factors to the square root of the first term, the sign from the middle, and the square root of the last term. And 5 minus 3 is plus 2. What's nice about this form, it's called vertex form, is this is going to tell us that the vertex of the parabola is at 1, 2. So if I wanted to graph this parabola, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, sure. We're going to graph the vertex at 1, 2. It's right there. The other thing I can do to get an idea of what's going on with this graph, drop my black pen. The other thing we can do is if we go up a little bit higher, maybe, we can find out that the y-intercept, if I make the x equal to 0, we get 0 minus 0 plus 5. That tells me that there is an x-intercept or y-intercept at 5. 1, 2, 3, 4, 5. And since a parabola is symmetrical, if I go down 3 over 1, I can go over 1 and up 3 to get the next point. And that's going to help me kind of get the shape of my parabola right there. Any point on this parabola is a solution to this. We say a graph is a picture of the solutions. And so that is how I would graph the parabola, the quadratic. And so I did a couple graphs for you. I didn't know which type of graph you specifically wanted to see. So if you want to see another specific graph, we could do a graph by tables. We can do a graph by sine, cosine. We can do phase shifts, all sorts of exciting stuff. If you want to see a different type of graph, let me know in the comments. I see a couple great comments coming in, though. Let's see if we can answer another question. Wow, they're coming in fast. So keep those questions coming in. They're coming in from Twitch, Instagram, and TikTok. So keep those coming on. That would be great. How can I complete a fractional function? I don't think I know what you mean by a fractional function. Do you mean like a fractional exponent? We can work with a fractional exponent. So exponents that are fractions work just like any other exponent. So let's say I've got x to the 5/3 times y to the 1/2 over x to the 1/6 times y to the 3/4. Like, we can deal with fractional exponents, and that's still the exponent rule that we've seen before is still going to apply. So if we've got x on top and bottom, we're going to subtract these exponents. So as we subtract, we need a common denominator. Let's get a common denominator of 6 by multiplying by 2. 10/6 minus 1/6 is x to the 9/6. And on the y's, I'm going to get this to have a common denominator of 4. So we're going to multiply the 2 by 2 to get 4 and the 1 by 2, 2. 2/4 minus 3/4 is negative 1/4. And then this is going to allow me to simplify x to the 9/6. We can reduce that fraction to 3/2 by dividing both of them by 3. The y to the negative 1/2, a negative exponent just tells us it needs to move down. And so we end up with y to the positive 1/2 for our final solution. So that's one thing we can do with rational exponents. The other thing we can do is we can actually simplify some expressions. So let's take a look at doing that. And as we do, don't forget, this is your live office hours. So what problem concept do you want us to do next? Stick it in the comments, and we're having a lot of fun answering as many of those questions as we can. If I don't get your question right away, I still have it. Stay tuned. We'll get to it as quickly as possible. So if I wanted to do like 8 to the 3/2 power, what that, actually I want to go 2/3 power. 2/3 power. What that fractional exponent actually means is this denominator is the index on a radical, and then we put the exponent on that. So if we do it this way, 1 second. There you go. Like my little water bottle a student gave me, it says Wallace. How do I turn it? There, Wallace. Isn't that cute? At Wallace STEM, that's my handle. To evaluate this, we've got the cube root of 8. The cube root of 8 is 2. So this part simplifies to 2, and then we can square the answer, and 2 squared is 4. So that's how we can evaluate 8 to the 2/3 power, by taking the denominator as an index. Excellent. Keep those questions coming in. I see a question about graphing sine and cosine graphs. That's kind of a pre-calc concept. So let's take a look at graphing sine and cosine graphs. Those can be even more fun. I think I've got an example here. Yes, there it is. We're going to do y equals 3 sine of pi over 2 times x minus 1 plus 2. We're going to graph this one. And as we're graphing a function, we need to really identify what each number is telling us about the function. This number in front of the sine, that's the amplitude. That tells us how far up and down from the midline the graph is going to go. So whenever we establish where the midline is, we're going to go up 3 and down 3 from that midline. The next important piece of information on here is that pi over 2. That helps us figure out the period, or how long it takes before the graph starts to repeat itself on that sine curve. The period is always 2 pi divided by this number up here, which is pi over 2. But when we divide by a fraction, that's the same as multiplying by its reciprocal, which is going to allow the pi's to reduce, giving me a period of 4. So every 4 units, it's going to repeat. It's going to hit the top, middle, bottom, middle, and then repeat. What's nice is there's kind of 4 pieces to a sine graph. There's the middle, and there's the top, and there's the middle, and there's the bottom. And then it starts repeating, 4 pieces. So those 4 pieces divide in here nicely. We're going to be able to see that basically, as we graph it, there's going to be 1, 2, 3, 4 units. It's going to be perfectly aligned there. So that's going to be nice. That's going to be helpful as well. The other important piece of information on here is this -1 inside the parentheses. That's going to give us a horizontal shift that's equal to 1 to the right. So this graph is not going to start at the axis like it normally does. We're going to shift 1 to the right. The next piece of information that's important is this +2. That +2 at the end tells us what's happening to the midline as everything's coming off. The midline has a vertical shift of up 2 units. I guess the only other piece that we didn't really talk about was the fact that this is a sine graph. Sine graph is going to start at the midline. So in this colorful array we've got on here from this equation, we've pulled off lots of important information that's going to help us actually get the graph of this function. So let's see if we can graph it. Drop my pen again, 1 second. And back. Should do some type of like going down the stairs. That might be more entertaining. I don't know. We'll see. Let's graph this guy before I get way off topic. Okay, here's our axis. We're going to eventually go up 2, so let's start a little bit lower than one would expect. And 1, 2, 3, 4, 5 that way. 1, 2, 3, 4, 5, 6, 7, 8, 9 that way. That gives us plenty of space. All right. We said the midline is a vertical shift up 2. So let's show where that midline is now here at 2. This isn't actually part of the graph. It's just going to help guide us that that's the middle of the graph. The other thing I can see is the period was 3. That means we're going to go up 3 and down 3 from that midline. So let's add another guideline, up 3 from the midline and down 3 from the midline. So I know it's going to kind of be centered on this green line. It's going to oscillate up and down, doing its sine thing from there. Horizontal shift is 1 to the right, and it's going to start at the midline. So I'm going to go 1 to the right and start right on the midline. And then we're going to make our graph knowing that the period is 4. So by the time I go 1, 2, 3, 4 over, it's going to start repeating there. And that's going to repeat every 4. 1, 2, 3, 4 over. It'll repeat even backwards. 1, 2, 3, 4. It'll start repeating. And it's going to repeat. We split this into 4 parts. The middle one, we're back at the middle. The first one, we're at the top. The next one, we're at the bottom. So we're literally going every one top, middle, bottom, middle. Going backwards, top, middle, bottom, middle, top, middle, bottom, middle, every one. And so when I connect these dots, we end up with this nice, beautiful sine curve that you asked us to graph. This then is a picture of all the solutions to the original equation. Excellent. Keep those questions coming in. I see a request to do the addition method next. I think you mean like solving a system of equations with the addition method, or it's also called the elimination method. Let's take a look at that. I also see some great calculus questions coming in. I am going to take note of all the calculus questions that come in, and I'll start off our calculus study session tomorrow with those questions. But this study session today is for your algebra and pre-calc questions. What are you wondering about functions, about conic sections, basic matrix operations, radicals, factoring? What else is in there? Solving equations, solving higher ordered equations, rational root theorem. How do we factor something big and ugly? Conics, logs, exponentials, all those things are in pre-calculus. Those are what we can take a look at and answer your questions. All right, so I said we were going to do some addition method. So let's do 5x minus 3y equals 4, and 2x plus 2y equals 7. Let's see. This one's probably going to have fractions for answers, but that's okay. We can handle fractions. Fractions are friends. Many people think fractions are the F word of mathematics. Not true. Fractions are friends, not food. Food. What were you thinking was the F word of math? Never mind. Let's solve this problem. All right, so with the system of equation, with the addition method, the idea is we want to add these together so that one of the variables is eliminated. To get a variable eliminated, we need opposites in front of one of the numbers. We can pick either one to pick on. Do we want to pick on x or do we want to pick on y? Let's kind of show how both work so we get an idea of what's happening. If I want to pick on x, we see the least common multiple of 5 and 2 is 10. So I'm going to make one of these positive 10 and one of these negative 10. Let's make this first one positive 10. We get that by multiplying by 2 on both sides. We're going to make the bottom one negative 10. We get that by multiplying by negative 5 on both sides. When we multiply by that, what does our equation come? Well, let's distribute. We have 10x minus 6y equals 4 times 2 is 8. Distribute the negative 5 through. Gives us negative 10x, negative 10y equals negative 35. When we add these equations together now, because we've done that addition method, these 10x's are going to eliminate and go away. 10 minus 10 is 0. We're left with negative 16y's equals negative 35 plus 8 is negative 27, I think. Yep. And then what we'll do is we'll divide both sides by that negative 16 to get the y by itself. And y is equal to a negative divided by a negative is a positive. I said it was going to be an ugly fraction, but we found out y is 27 over 16. Now that we know what y is, we can plug it into this equation to solve for x, but dealing with that ugly fraction is going to be kind of a pain. So rather than dealing with the ugly fraction, let's do elimination again, but this time let's eliminate the y's. So same exact process. We're going to hold on to our solution for y. We already got that. But now let's go through and let's eliminate the y's. So the idea is we want to get opposite numbers in front of y. 2 and 3 both have a multiple that's 6. The least common multiple is 6. So we're going to multiply the negative 3 by 2. That's going to give us negative 6. And the 2 by 3, that's going to give us a positive 6. So now this equation becomes, when I distribute the 2 through and the 3 through, 10x minus 6y equals 8. And 6x plus 6y equals 21. And this is really nice because I can add these functions together, and the y's will eliminate when we do that addition step, giving us 16x equals 21 plus 8 is 29. And then finally, we can solve by dividing both sides by 16. And x is equal to 29 over 16. So now we have our x and our y solution for this system. Great question. The addition method, great way to solve. It's probably more straightforward and quicker than like the substitution method, less to keep track of. It solves quicker, but it does take a little bit more work to set it up correctly. So that's kind of the trade-off that we get. All right. How do we do the domain of a tangent function? Great question from Lily on TikTok. Let's hop over to a little bit of trig and take a look at the tangent function, and we'll talk a bit about the domain on that tangent function. So with tangent, the way I like to think about tangent is start by thinking about the unit circle, right? How'd I do on my circle? It's a little pointy. My circles are terrible. Don't judge me. All right, so the tangent, we know the tangent of the function, or the tangent of any angle. Let me get a deeper orange here. The tangent is the sine over the cosine. Sine is the y, cosine is the x. So tangent, I'll go ahead and outline this again so that it shows up a little better. Tangent is defined whenever y divided by x is defined. What does that mean? That means we can't have 0 on the bottom of a fraction. So whenever x is equal to 0, or whenever cosine of our angle is equal to 0, that's when the tangent suddenly becomes undefined. It doesn't really matter what y is, but when the x or the cosine is 0, then we end up with an undefined tangent. Well, x is 0 on the unit circle, up there and down there. What is up there? Think about your unit circle. That's going to be our pi over 2 point. What's down there? That's 3 pi over 2. That means in one revolution of the circle, tangent is going to be undefined at pi over 2 and 3 pi over 2. And since that's exactly 1 pi away, right, we can just add pi, and then we can add pi. Every pi, we're going to end up with another undefined point. So the tangent of theta is undefined whenever theta is equal to pi over 2 plus some number of pi's. Because every 1 pi, we get another solution, where that number is any integer. That funky symbol means integer, means -1, -2, -3, 0, 1, 2, 3. But anytime we have pi over 2 plus some number of pi's, tangent is going to be undefined. Excellent. Let's look at some solving of tangent. Solving of tangents. How do you find the exact value of an inverse trig function? Yeah, let's do that. We're kind of spending a lot of time on trig. Remember, pre-calc and algebra is going to include a lot of other things too. So if you want to see some of those other topics, you need to put a vote in for it. Put it in the chat. Tell me you want to talk about domain. Tell me you want to talk about functions. Tell me you want to talk about logarithm equations, exponential equations. What do you want to see? Give me a specific problem you want me to solve. Stick it in the chat. We'll take a look at it. But the question came up is, how do we find the exact value of inverse trig functions? Well, it depends. Is it a point that we actually know the solution to? For example, the tangent inverse of the square root of 3. Square root of 3 is a point that we know about on the unit circle. I like to think with tangent because tangent's a little hard for me to get my brain around. I'm really good with sine and cosine, but tangent's always a tricky one. So if I think about that square root of 3 as a fraction, I put that square root of 3 over 1. And I can do anything to the top and bottom of that fraction. So we're going to take the square root of 3 and divide by 2. And we'll take the 1 and divide by 2. What's nice is we know tangent is sine over cosine. Or more specifically, if you want to go even further with it, it's going to be sine is the y and cosine is the x. And so by dividing both of these by 2, it's telling us exactly where on the unit circle we want to be in order to answer this problem. We want y to be root 3 over 2, so we got a bigger y. We want x to be 1/2. So if I go 1/2 root 3 over 2, I'm at this point right here. And so I'm actually talking about the angle pi over 3, which is up there. So tangent of root 3 is actually equal to pi over 3. But, oh, I see a question for completing the square. That's one of my favorite topics. We'll do that one next. A lot of the times we don't have one of those key points on the unit circle that we like. Instead, it's asking for like maybe the sine of the cosine inverse of 3/5, right? Well, what's nice is cosine inverse is saying we're looking for an angle. What angle has this relationship of 3/5 on the cosine? So if I think about the triangle in this case, rather than the circle, where this is the angle I'm talking about, if the cosine is adjacent over hypotenuse, my adjacent is 3 and my hypotenuse is 5. Now I can use the Pythagorean theorem, a squared plus b squared equals c squared, to figure out this missing side. C squared's 25, b squared's 9. 25 minus 9 is 16, which has a beautiful square root of 4. Sine wants to take the opposite over the hypotenuse. In this case, the opposite over hypotenuse is 4 over 5. And so we've evaluated what the sine of the cosine inverse is without even having to worry about what is the cosine inverse of 3/5, which is a really nice, slick trick. All right. I mentioned my favorite topic. One of my favorite topics out of algebra is completing the square. And we can use completing the square to do lots and lots of things. We can use completing the square to help get our conic sections into standard form so we know where the vertex is. We can use completing the square even in calculus to help us integrate into a tangent inverse form. And we can use completing the square to solve an equation. I'm going to focus really on just the completing the square process, which can show up in any of those contexts. But I'm going to specifically focus on the process in such a way that we can't factor or use the quadratic formula. So let's say I've got 4x squared minus, should we do one with fractions? I want to show you how easy it is with fractions. It's not too bad. People get kind of scared with fractions. It's the F word of mathematics. Fractions are friends, not food. Friends, we can do this. So we're going to do one with fractions. Let's do 6x plus 7. Now, first thing I want to notice is there's no equal sign here. We cannot use both sides of the equation. There's no equal sign. You can't create one. Don't cheat. Don't do that. What we can do, though, is we're going to group together the things that have x on them. And then we're going to get rid of whatever's in front of x squared by factoring the 4 out. We're going to force factor that out, which means we're going to divide the 6 by 4 also. 6 divided by 4 is 3/2. That's okay. We're going to force factor it out. Fractions are okay. Remember, fractions are friends, not food. Add 7, because that's still there. We haven't done anything with the 7. Okay, the whole crux of completing the square, what makes completing the square works, the thing that you need to know how to do is to get that magic number that's going to make this into a perfect square so that we can factor it. The way we get that magic number is we are going to take half of whatever's in the middle, which is 3/2, and then we're going to square that answer. Well, half of 3/2 is 3/4, and if we square that, we get 9/16. That's the magic number that's going to complete our square. So we're going to add that magic number of 9/16 inside the parentheses. But if I add it to stay balanced, we need to balance it out by subtracting out the 9/16. Now, little word of warning, common error here, we want to make sure we avoid it, is that 9/16 isn't just a 9/16 by itself. There's a 4 in front of the parentheses. That 4 is going to distribute into the parentheses, which means it's actually going to get multiplied by the 9/16. So we also have to multiply the 4 by the 9/16 over here. When we do that, we've got a 4 out in front. This we know is a perfect square. It's going to factor to something squared. We take the square root of the first term, which is just x. We take the sign from the middle, and we can take the square root of the last term. The square root of a fraction is just 3/4. For square root of the top and the bottom. What happens over here? Well, let's do a little simplifying. 4 over 16 is going to reduce to 4, so I've got 9/4. We're subtracting. We need to get a common denominator. So I'm going to take the 7 and multiply by 4 over 4. So we have 28 minus 9 is 19 of these fourths. And we've completed the square, and now we've put this original quadratic in really to what's vertex form. The vertex is at 3/4, 19/4, and we could go from there. If this was equal to 0, which it wasn't to begin with, you can't do this, but let's say it was equal to 0 the whole time, you'd be able to subtract the 19/4, divide by 4, and take the square root of both sides to solve for x, and it solves really nicely and quickly. Completing the square is really useful to us in order to get into a standard form that we can work with, and it opens up so many more opportunities for us than just the quadratic formula or just the factoring methods that we've seen before. This one, quadratic formula, would be ugly. Factoring is impossible. So I really like completing the square. It takes some getting used to and does create fractions, which scares some people, but I promise you, once you practice and get good at it, it's going to be the better way to go. All right. Why am I subtracting it from 7? Good point. So we want to stay balanced, right? There's a 7 here in the original problem. That I didn't do anything special with that. That's from the original problem. So the idea is, since there's no equal sign, we can't do the same thing to two sides of the equal sign. We need to know, but we need it to stay balanced. So if I add something in to stay balanced, I also have to subtract it out. It's kind of like if I give you $5, but we don't want to change how much money we have. If I give you $5, you have to give me 5 ones. So we stay balanced. So we have the same amount of money between us. So you gain 5 and you lose 5, but now you've got a $5 bill and I've got 5 ones. So they're different and separate. Brennan on TikTok, you're just being stubborn, sticking with quadratic formula. I'm sorry. This is better, and it does more things. It's going to get you further in math. I promise it'll be worth learning it. I promise once you do a couple of these, practice them, get good at them, this process is quicker than the quadratic formula, and that's why I really like it. All right, I got a question from TikTok wanting us to do some practicing with factoring. So let's do a little bit of factoring. We can't do an algebra review without talking about factoring, because factoring is so fundamental to really everything we do in mathematics. The reason is terms, which are added things, 5 plus 2x plus x squared, terms, you can't do much with them. You can't reduce them in a fraction. You can't reduce them in a radical. You can't split them up in a fraction. Terms are annoying. Factors, you can do so many things with. So we want factors. So if I've got something like 6x squared plus 7x minus 3, if I could factor it, we could do a lot more with it. Now, there are lots of ways to teach factoring. My personal favorite is slide and divide, but there's also methods like the AC method. There's methods like the box method. Some people do a guess and check method. It really doesn't matter which method you use, as long as you find a method that works for you and you can do it successfully. But I'm going to show you how to do divide and slide. If you want to see one of those other methods, stick it in the chat and I'll try and do one of those other methods, whether it's box, AC, guess and check, let me know. But this is how slide and divide works. It's so slick. The idea is this thing is going to be more difficult to factor. Let's simplify it by sliding the 6 into the 3. So we have x squared plus 7x, and 6 times negative 3 is negative 18. That's going to give me a trinomial that's easier to factor. And so I'm going to factor this easier trinomial. So to factor it, x squared is x times x. We need two numbers that multiply to 18 and add to 7. Well, 18 is 6 times 3, but I can't get 7 with those numbers. 18 is also 9 times 2. 9 times 2 can give us 7 if the 9 is positive and the 2 is negative. And a positive times a negative is a negative. So if that's the case, then that, be careful here, that is not the answer. That is the blue line factored. We wanted to factor this first line, the black line. I said this method is called slide and divide. We did the slide of the 6. Now we're going to divide by the 6. I'm going to divide by, that's a 5, not a 6. I'm going to divide by 6 each of these numbers. And then I'm going to reduce it. Actually, I'm going to do it in black so it's a little easier to see. Maybe orange. Orange might be easier to see. Well, that doesn't contrast. I'm doing it in black. So many important decisions. We're going to divide by the 6 that was slid over. When I divide, I'm going to reduce these numbers. Once it's reduced, whatever's left in the bottom is going to go in front of x. Whatever's left on top stays with the plus or the minus sign. 9 over 6, divide those both by 3, we get 3 over 2. So I'm going to put the 2 in front, and so we have 2x plus 3. 2 over 6, reduce that. Dividing by 2 gives us 1/3. I'm going to put the 3 in front, 3x minus 1, and now it is factored. That is called slide and divide. Jack on TikTok, exactly right. 9 and -2 were the numbers that made it work. Great work. Excellent, excellent. All right. Let me know if you want to see more of those. A lot of great questions coming in. We needed help with factoring. We just did that. We did quadratic equations. Let's see, what else? AP pre-calc. How do I memorize the unit circle? Lily on TikTok. Memorizing the unit circle is so important. I'm so glad you brought this one up. There are lots of tricks to memorize the unit circle. Let's cover some of my favorites, and then hopefully that will help you remember the unit circle. Okay, so here's my circle. Woo. That is a terrible circle. Don't judge me. All right. Let's see. What I think about first when I want to get my radians on the circle, for example. To get my radians on the circle, I think about a clock. A clock has noon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 on the clock, right? On the clock, we have got all of the pi over 6s. Starting from 0, because that's where the unit circle starts, you've got 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, and 11 pi over 6. Now, some of those do reduce. So let's go ahead and reduce the ones that reduce. So 2 pi over 6, I can divide by 2. That's going to be pi over 3. 4 pi over 6, I can divide by 2. That's 2 pi over 3. 8 pi over 6, I can reduce by 2. That's going to be 4 pi over 3. 10 pi over 6, I can reduce. That's 5 pi over 3. And then I guess this is technically 2 pi. But the other ones that we can reduce are on the corners. This would have been 12 pi over 6, which reduces to 2 pi. At the top, I can divide these by 3. That gives me 1 pi over 2. Over here, 6 pi over 6 reduces to just pi. At the bottom, dividing by 3 gives us 3 pi over 2. And then we've got most of the unit circle in there. What is missing is the quarters. Fortunately, the quarters happen every quarter. So I'm going to put a quarter, a quarter, a quarter, and a quarter in there. In those quarters, those are the pi over 4s, and they're all the odd ones. 1 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And that's how I fill in my quarters. Now, what about the coordinate points? I'm running out of colors. I need more bright colors. Oh, brown. Here we go. Rolled away on me. For the coordinate points, I know these on the axis, those are the easy ones, because I can just count off. I know it's a unit circle, so it's a distance of 1 in the x direction and then 0. This one is 1 in the y direction, so 0x, 1y. This one's backwards, so it's -1, 0. This one's down, it's 0, -1. Those are the easy ones. Kind of off screen, but you can see it. For all the other ones, the options are either 1/2, √2/2, or √3/2. They count up. Technically, this is the square root of 1 also. It's just been simplified. Square root of 1, square root of 2, square root of 3/2. If I'm talking about a longer distance, that's a long x distance, I use the longer number of √3/2. If I'm talking about a shorter distance, I use the shorter distance of 1/2. Here, this one's right in the middle. So it's not long or short, it's right in the middle. That's the √2/2. And it's the middle distance both in the x and the y direction. This one, we've got a short x and a long y. So the short x is 1/2. The long y is √3/2. And you can keep that pattern going around the circle. And that's how I can figure out the entire unit circle. Now, I've heard people do the hand trick. Let me see if I can replicate the hand trick here. Notice your hand kind of maps out the first quadrant of the unit circle. Let me zoom in my hand. If I assume my hand is the first quadrant of the unit circle, cosine is going to count up. Cosine is going to count down. You've got the square root of 4, 3, 2, 1, 0/2. Sine counts up. It's the square root of 0, 1, 2, 3, 4/2. And that gives you all of the points on the unit circle. So lots of ways to kind of keep track of and memorize the unit circle. Really, practice is the best way to get good at it. Use the numbers, draw the unit circle, practice, 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 and you can get it. All right. Let's see what other questions we have. We want to look at factoring using synthetic division. Let's do some synthetic division factoring problems, also called the rational root theorem. Oh dear, my brown doesn't erase. Well, if I scrub at it really hard, it's going to go away. This is your office hour focusing on algebra with Che. We are excited you've joined us. If you have any questions about algebra or pre-calculus, stick them in the comments and we will do our best to answer them as part of this hour. We are here every week, every Wednesday at 5 o'clock Pacific time, 8 o'clock Eastern time. So mark your calendars if you're taking algebra or pre-calculus. This is the place to get your questions answered live, online, every week. Let's say we want to factor x to the 4th minus 3x squared. That one's a little obvious. I'm going to pick a different problem because it's too obvious. I don't want to do an obvious one. That one you can do by hand. Let's find a rational root theorem problem in this textbook. Here I have rational root theorems on page 170. Stay tuned. This is going to be a fun one. All right. We are going to try and factor 6x cubed minus 19x squared plus x plus 6. And I just pulled this one randomly out of the book. So let's see what we end up with. All right. The idea of the rational root theorem is we're going to start with factors of 6 to see if it might be a factor of this problem. So factors of 6 are 1, 2, 3, and 6. And they might be positive or negative. So the way we're going to find out if they're factors is we're going to use synthetic division, starting with the 1, and we're going to take it into this expression. We'll take the coefficients of 6, -19, 1, and 6. The way synthetic division works is we bring the first number down, multiply by 1 to get 6, and then we add these together to get negative 13, times 1 to get negative 13, plus 1 to get negative 12, times 1 to get negative 12, and we end up with negative 6. If we end up with anything besides 0, that means our number did not work. 1 doesn't work. Let's try negative 1. See if that changes things. Bring down the 6. 6 times negative 1 is negative 6, gives us negative 25. Negative 25 times 1 is 25. You can already see this is not going to work. It's way too big. 1 is out as a candidate. Let's try the number 2. All right, bring the 6 down. 6 times 2 is 12. 12 and negative 19 is negative 7. Negative 7 and 2 is negative 14. Plus 1 is negative 13. Times 2 is negative 26. That's not going to give us 0 either. Hopefully one of these is going to work. 2 didn't work. Let's try negative 2. Okay. Bring the 6 down. 6 times negative 2 is negative 12. That's going to give us a positive 31. Oh, this is not going to work because that's going to be negative 62. That's way too big. All right, 2's out. Hope I picked one that was possible. Let's try 3. Bring down the 6. 6 times 3 is 18. 18 minus 19 is negative 1. Negative 1 times 3 is negative 3. Negative 3 and 1 is negative 2. Negative 2 times 3 is negative 6. 6 and negative 6 is 0. That's the number we were looking for. It finally happened. Okay, so the synthetic division gets us down to 0. That was our goal. What does that tell us? It tells us that x equals 0 would be, or x equals 3 would be a solution. If I subtract 3 from both sides, x minus 3 equals 0. Tells us that one factor of this expression up here is x minus 3. To get the other factor, looking at what's left, we've got negative 2, we've got negative 1x, and 6x squared. In other words, we've got 6x squared minus x minus 2 to factor. Well, this is another great opportunity to practice divide and slide. Let's slide the 6 over to the negative 2, giving us x squared minus x minus 12, because this is easier to factor. So let's factor that easier expression. We want x times x to get x squared. We want to multiply to negative 12, which we can do with negative 4 and positive 3, because that's going to give us negative 1 in the middle. Be careful, though. It's slide and divide. Don't forget to do the divide step. We slid the 6. Now I'm going to divide by 6. Reducing these fractions, the denominator comes up and the numerator stays there. So 4/6 reduces to 2/3. Bring the 3 out front. We get 3x minus 2. 3/6 reduces to 1/2. Bring the 2 out front, and we're left with a 1. We've got 3x minus 2, 2x plus 1, and our other factor is x minus 3. We're not going to forget about the 1. We did all that work to find. We have now factored this big polynomial using synthetic division and also that rational root theorem that tells us good candidates to pick are factors of this guy, this last term. Other candidates that you can pick, if we had run out of 3 and 6, we can take factors of the first term divided by factors of the last term. So we could do 1 divided by 6, 2 divided by 6, 3 divided by 6, 4 divided by 6. And notice you get 1/2 and 2/3 as options. Those would have come from those rational options as well. Question came in from Steph on TikTok. Where did I get the numbers 1, 3, 6 from? All based on the constant term. I look at factors of the constant term. Those are usually good candidates for the factor that's going to be here. So 1, 3, and 6, 1, 2, 3, and 6. Don't forget to check the negatives. I probably should have said plus or minus, plus or minus, plus or minus, plus or minus. But that gave us 8 good candidates where we were pretty sure one of them would work. Took 5 tries to find one, but we found one. What's nice about synthetic division is it's pretty fast, so you can check really quick to see if that is the correct answer. Excellent. Well, I got a question for some trig identities. I think we've got time left in our hour to do one trig identity together. Remember, we are here every week at this time, every Wednesday, 5 o'clock Pacific time, 8 o'clock Eastern time. Mark your calendar so you can join us again next week. If you're looking for some calculus fun, we're going to be doing that tomorrow, I think at 4:15. If you want to see the full schedule of Cheg's review sessions, scan this QR code up here, and we'd be more than excited to share that with you so that you can join us throughout the week for all the great lives that Cheg does. All right, let's take a look at, what would be fun to do? Let's do sine of theta minus cosine of theta. And we're going to divide by secant of theta minus cosecant of theta. And we're going to prove that that just equals the sine of theta times the cosine of theta. The big strategy that we want to employ for trig proofs is we're going to work just on one side and simplify it to look like the other side. What do we simplify? Well, if you don't have any clue what to simplify, what I would simplify is change anything that's not a sine or cosine into a sine or cosine. So we've got sine theta minus cosine theta in the numerator, right? In the denominator, though, secant is the reciprocal of cosine. Cosecant, we know, is the reciprocal of secant. And when I do this trick, invariably, almost every time, you will end up with little fractions inside of a big fraction. I wrote secant, not sine. I said sine. Cosine is the reciprocal. Cosecant is the reciprocal of sine. There we go. When we end up with these little fractions inside the big fraction, almost always our next step is going to be to clear those little fractions by multiplying every term by that common denominator. In this case, that common denominator is cosine sine. We'll multiply it on top and bottom to stay balanced. And when we distribute it, it's going to go onto each one. There we go. Sine reduces with sine, cosine reduces with cosine. So we end up with cosine theta. Sine theta times sine gives us sine squared theta. Cosine times cosine gives us cosine squared theta times sine theta over our common denominator of sine theta minus cosine theta. All right. Now that we've made it into a simplified fraction that just has sines and cosines on it, we're ready to take a look at how we can simplify it. What we can't do is reduce cosines and reduce sines. That's bad. The reason is it's not factored. We can only do that type of stuff with factors. We don't have factors. Well, we can get factors. Let's factor that numerator. Factoring out, both of these have a cosine and a sine. Let's factor out cosine sine. Cosine theta, actually let's write it as sine cosine, just because it's prettier that way. Sine cosine. When we factor out a sine and a cosine, we're left with a single sine. Minus. Factor out a sine and a cosine, we're left with a single cosine. Divided by sine minus cosine. And now that it's factored, now we notice we've got this common factor on top and bottom of sine minus cosine. That is beautiful because that can reduce out, which is just going to leave us with sine cosine, which is what we want. QED. Let's That's Latin for that which was to be demonstrated, quaeream demonstram. Or you could do the little black box, or you could just say proof done, however you want to do that. Well, there are so many great questions coming in the chat. Financial algebra is lots of fun. Disk and washer methods, logarithmic equations, more trig identities, so many more things to take a look at in our review of algebra and pre-calculus. So I hope you can join me next week when we do more algebra and pre-calc questions. We are here every Wednesday at 5 o'clock Pacific time, 8 o'clock Eastern time. Make sure you join us for that. Also, those of you that were looking for some calculus answers, that's tomorrow. Scan the QR code and I'll see you tomorrow for that. The calculus review is at 4:15 Pacific time at 7:15 Eastern time. I want to thank you all for joining me, though. Your engagement and questions have been so much fun. I love sharing my passion and love for algebra, pre-calculus, and really mathematics with you. Before we go, don't forget to check out chegg.com. They're here to support you 24/7, really, with all your toughest subjects and doing lots of things to support you like these lives, but also other great support from experts. And we are here also on TikTok, Instagram, YouTube, Twitch. Follow Chegg, follow me at Wallace STEM, also on those various accounts. We're here every time this week, 5 o'clock Pacific time, 6 o'clock Eastern time, every Wednesday doing algebra and trig. I look forward to seeing you all next week. Until then, happy studying. Rate winners, yeah.